it's a pleasure to introduce you to Photolytics. So we have here today Martin Veni. He will talk about LS2G, novel versatile multi-line scan global shutter sensor family. So please, the floor is yours.
Thank you very much for having me here, and welcome to my talk about line scan sensors and global shutter sensors, and especially the LS2G line scan sensor family that we present here for the first time at the Vision 2021 in Stuttgart. So maybe you have not heard about Photolytics before, because we incorporated just in 2018, so the last Vision that was actually held before we all went in some strange remote work mode and texted over all sort of channels. But we're actually a team of image sensor engineers or fanatics that have some experience coming from IMEC, CSEM, myself from Aweba, Photon Focus. My colleagues come from OmniVision and CMOSIS, IMEC. So we have all worked together at CMOSIS, respectively Aweba, which went together in 2014, and 2015 became part of AMS, which was not so much my cup of tea and not the one of many others. So 2018 we founded Photolytics in a beautiful town of Ruze in Bulgaria, and there we focus on really specialty sensors, so the industrial market, medical, scientific imaging, high-speed imaging. So these sort of things that the big industry giants with the main focus on the mobile phone and mass markets would not do, but which we believe that has a place in this industry and does create additional value, that does save lives, that does make our food better, that does make us better products and generate less waste in the production process. So I will talk about recent CMOS image sensor pixels and things that have been developed and come to more maturity in the last 3 years. Then I talk about the LS2G line scan, multispectral line scan sensor family. I explain a little bit the resolution variations that we have, the pixel variations that are there with the black and white, RGB color modes and the infrared modes, and then packaging. And I will also talk briefly about the timeline which we see to roll out these sensor families. And I hope to speak sufficiently fast to have time for the questions and answers, which I'm sure will come, and many questions as usual. So in terms of global shutter pixels, we have basically 2 families of global shutter pixels that are known in the market and have come to a good level of maturity and pixel performance. So first of all are the charge domain and global shutter pixels. That's basically a CCD in a CMOS process. So when I started with imaging back in '96, we thought CMOS imaging would permit us to use standard logic processes. We're far away from that. We have basically integrated in CMOS all the features of good old CCD. So we have buried channel devices, we have buried channel transfer, we have lateral overflow gates, and so on. So at Photolytics, we have recently finished the development of a charge domain global shutter pixel that we published at ISSV, where we have a shutter efficiency of over 90 dB and about 2 electrons read noise. So that's basically a 3-electrode CCD. You can see in the animation how the charge is collected in the photodiode and transferred to the memory gate. Don't know if I have don't think I have a laser pointer on this. And then it is transferred when you address the pixel to the readout mode. Next. Then we have the voltage domain global shutter pixels. So that's basically you have a photodiode, you have a transfer to a floating diffusion where you convert the charge to a voltage, and then you have a sample and hold stage to capture and store that voltage until you read it out. Especially these pixels, they have some advantages over the charge domain pixels if you have space, as is the case in line scan sensors, where you can put the sample and hold next to the photodiode and you do not lose a fill factor. First of all, these pixels offer even better shutter efficiency, 1 to 100,000 can easily be achieved. We have very good charge transfer. We can do binning and charge averaging in the periphery. And also what is quite important, these sort of pixels, they do not need complicated voltages as in a charge domain global shutter pixel, where you typically need negative gate bias voltages and controlled slew rates. So that's quite important for making high resolution line scan sensors, where the signals have to be toggled very fast, but only from the sides and over a long line. And it's ideal for line scan because, as I said, you have space to put the sample and Hall electronics aside of the photodiode, and it does not cost fill factor. So that's what we integrated in the LS2G line scan sensor family, which is organized here in blocks of 2K pixels. Each of these 2K pixels has 8 LVDS-bit serial taps that currently we run at 900 megabit per second. We think with the small redesign of the sensor, we'll get to over 1 gigabit per second to speed the line rate even further. We have, for the 7 micrometer resolution, we have blocks of 1462 pixels, so that fits to the same length as 2K on 5 micrometer. And then we also have dual pixel interlaced modes to cover the 3.5 micrometer type of applications for the very high resolution line scan sensing. Then you get the double of the 7 micrometer pixel. So the LS2G sensor is really meant to cover with one sensor a multitude of different applications. That's why it's not a single line sensor or a trilinear sensor. It's actually a sensor which has 32 lines. We don't expect that an application will use all of these 32 lines at once, but depending on the application, you can choose some of these lines to work. If you have just a monochrome high-speed scanning application, you use one of the monochrome lines. If you have a color application, you use 3 of the lines for RGB. You can add a clear channel, so to have a higher sensitivity without the color information, or you can use a near-infrared only channel, and then depending on the resolution requirements, you can use 5 micrometer pixels or 7 micrometer pixels. So this sensor is meant to overcome a little bit the problem of line scan, which is the niche of industrial machine vision, which is actually already quite a small niche of the whole imaging world and industry, where if you compare our industrial volumes to mobile phone modules, we're really very, very small, even high-running products, and line scan is maybe 20% of the industrial vision. And then if you look at color line scan, that's maybe 20% of the 20%, and if you look at multispectral line scan, that's maybe 5% of the 20%. So it's very few applications, and it's not worth each time to make a dedicated sensor, and it's also not worth each time to make a dedicated camera. But we think with this flexible architecture, we can actually enable many more applications to be addressed in a good way by having a hardware that is there, that is made, and then it can be configured for the very specific applications. So here the slide that it is what we have on 7 micrometer pitch pixels. Already explained it a little bit. So in terms of line rate, which is very important for obviously a line scan camera, the sensor is organized in these multiples of 2K segments on the 5 micrometer pitch, and therefore with all resolution variations you can reach the same line rates. So even at 16K resolution, the line rate is not 16 times lower than with a 1K resolution. It drops a little bit because overhead times increase for driving the sampling signals along this 16K pixel line. But at 16K, we have the prototype now where we achieve 300 kilohertz line rate. For the further planned resolution, where we want to make sensors with smaller resolution, in the pipeline is the 6K resolution and 12K resolution. We see from our data that we achieve 500 kilohertz scan rate at the 6K resolution, so that would be 4K with the 7 micrometer pixels, respectively 8K with 3.5 micrometer pixels. We also plan to have additional resolutions are possible if we see that there is a demand for those. In terms of the spectral response of these different lines, as I explained, we have the clear channel, so that's here the dark blue. Then we have the blue, green, red channels, the typical dye colors as you know them from RGB channels. And then as a specialty, we have this near-infrared channel only, which allows to combine some information that you cannot see in the visible. We see this type of applications, especially in food sorting, food processing, or in the printing industry. You can just see many more features when you combine near-infrared to the RGB visible channels, as opposed to only having the visible channels. It's not hyperspectral in a sense, you just add one more spectral channel, but actually this one more channel can provide a lot of additional information compared to the visible RGB channels. In terms of packaging, that's also something quite important, especially for the very high resolution sensors. You need to have a package which does not cost more than the sensor and which does not make your camera and the alignment mechanics to the lens more expensive than the whole electronics that sits in there. So that's a concept we've come up already over the experience to have these high resolution sensors on a mechanically very precise base plate, which is also a good thermal conductor. We've chosen a special ceramic plate here to bond the sensor to, and then because of the many high-speed LVDS outputs, it is much more convenient to have circuit board to route these signals and the board-to-board connector that is actually made for high-speed differential interfacing rather than a pin grid array package. This for the high resolutions like 12K and 16K modules, and for the shorter resolutions we have standard ceramic LGA packages for 6K and 2K modules, because they are more compact in space and allow to make very small cameras. But for the high resolutions, it's important to have a precise mechanical mount and a thermally very stable mount. So as I said, this is an announcement. We're not exactly yet shipping sensors. We have some sensors at lead customers that are developing and giving us feedback, and we will have the producible device for the 16K resolution in May next year, and then in June we will have the 6K package available and mass production for the 6K package in September next year, and the 12K will follow with 1 month offset. You can already see the 16K sensor up and running at our booth over there in hall, just on the other side of the TruePass booth B83 of hall 10. So I kindly invite you to come over, have a look, and add additional questions that you may want to pose in person rather than in the forum, so you will have a second chance. Otherwise, thank you very much for your attention, and I think we do have some minutes for questions and hopefully answers if I have them.
Thanks a lot, Martin. Thanks a lot. Yes, so let's start with again with an epic question. So you didn't have a specific slide like Matthias had, but I believe you might also look for cooperation. So look into, okay, you said you didn't ship yet, you are in an early phase of testing your products, but thinking about a second step, where do you see challenges? Where do you think you could have help from a collaborator, maybe from the EPIC network, but not only?
Well, definitely with LineScan, it's always a challenge to find the good applications, to actually integrate the product in the applications. I mean, with the multispectral, so with this addition of the near-infrared information, there is some applications that we know, but I think out there is a lot of additional applications in the field that actually could benefit from this additional information that can be achieved with the near-infrared channel only, which we may not necessarily know, they may even themselves not necessarily know that it would be beneficial. So I think that's something that will be challenging. Whenever you come with a new technology to a market, you see maybe only 5% of that market is aware when you develop the technology, because we're not academics, we do not develop technology just for the curiosity of it, but we always develop something when we see an application, but typically that's a very small part, and there is a huge market to be developed, and I think that's not something that we as a 12-people company can do ourselves. I think there we really are open to collaborate. We need other partners. We're working very open with camera builders, with system integrators to develop these new markets, to find these new applications. So I think that's one of the big challenges, to find really the 90% of the applications which can really benefit from this multispectral, I would call it, or visible plus. I mean, I do not doubt it hyperspectral, because typically hyperspectral, as we have seen before, is more like hundreds of spectral channels. But I think in between there, we have, with this multispectral approach, the advantage that we do not generate that much more data, so it can be handled with existing processing capabilities, but it still needs this new know-how, what to do with an additional spectral channel.
Yeah, so these basically, yeah, so integrators applications, you're open for ideas.
Exactly.
Then, going back to your slide, maybe you sounded very confident about the packaging that you are now providing. Is there something that you see that could be maybe in the future challenging and then you need support? For example, also on the volume. So at which volume are you thinking about? Is it something that the 12 people can deal with? And technology-wise, if you need some support on packaging, maybe in the future?
Well, packaging is actually an underestimated part of the imaging community. I mean, I've been probably 25 years in imaging, and 25 as a chip designer, and 25 years always fighting with packaging challenges. So it is a big challenge, and as the sensors get bigger, the challenge is also getting bigger, because you have to have those things clean. Pixels are shrinking, so the contamination, especially with chip on board, is relatively dirty technology. We do work with partners that have also a lot of experience in optical packaging, and actually doing this in a very clean way. Then also we have the irony that as sensor manufacturers for the industrial inspection industry, sometimes we see our subcontractors manually microscope inspecting for dust, which we found very ironic, and thought, well, maybe we have some customers of these sensors that could help you to automate this process. So it's sometimes quite funny how the world goes, but we're in that stream, and we're working constantly with packaging partners, with partners that supply materials like this ceramic base, which we actually developed from scratch for this sensor family, for a specific application where we need the sensor actually to be mechanically stable, thermally well coupled, electrically isolated. So there's a lot of specifications for something quite simple as a ceramic base plate.
But then it's good, because it means that it was a good question. So maybe we can talk about some other partners if you want to have, also through EPIC. So that is interesting to know that it was a good topic. So, and if there is no final questions, I guess we can thank all the three speakers again. So first, of course, Martin, but also Matthias again, and Peter from the beginning. So thanks a lot.
Thanks for having me. Thanks for moderating this session.
And yes, I guess we have maybe a couple of minutes of break, but the session is over. So thanks also from my side. And it was really a pleasure to work with the division organizers for this. And yeah, thanks a lot. And yeah, greetings from the full EPIC community. Bye-bye.